The number of intelligent civilizations in the universe is equal to the number of suitable for life planets, multiplied by the probability of origin of life, multiplied by the probability of intelligence among life. If you want to have a little existential crisis today, stand up, walk over to a mirror and really look at yourself. Look at all those bumps and black dots on your nose, arms and legs, hair and weird freckles. From the point of view of raw matter, atoms, molecules, all that stuff, you're basically a walking cosmic anomaly. You're a glorious, self-aware break in the grand uniformity of the universe. We love saying things like, snowflakes are a perfect example of nature's symmetry. Well, guess what? Snowflakes, ice crystals, frost patterns, those are not examples of symmetry. They're examples of breaking symmetry. Liquid water is more symmetric in all directions than its frozen cousin, meaning that when water molecules arrange themselves into ice, they actually lose some of that neat uniform isotropy. Ice forms repeating orderly patterns, so in essence, the crystal breaks the original uniformity of water. That's the big irony. What seems like a beautiful piece of symmetry is really a cosmic version of graffiti, matter deciding it wants to stand out, not blend in. Now let's scale up from your kitchen freezer to the entire universe. The universe on a large scale is pretty damn homogeneous. If you look around here, or there, or way over there, on average you'll see roughly the same stuff: galaxies, gas, or dust. But if the universe is so homogeneous, then what are you doing here? Just as ice breaks the symmetry of water, galaxies, stars, and planets break the symmetry of the universe. But nothing breaks it as much as by its existence as a human being. The sci-fi legend Stanisław once pondered in his monumental Summa technology: is our civilization an ordinary or an exceptional phenomenon? Do we correspond to the norms of evolution accepted in the universe, or do we represent an anomaly, an ugliness? We can figure out how water freezes into ice, and we can guess how galaxies and stars form, but come on, who can really explain how exactly we got here? After all, think about it. Just mentally transfer yourself 1 billion light years in any direction from where you are, and look around. The universe is the worst place you can think of for humans to exist. It's cold, empty, full of little radiation, and home to cosmic smashers like black holes. And yet here we are, breathing and complaining about taxes. Seriously, it's totally unsuitable. Is there any place in the entire universe outside Earth where you can teleport and not die? We could be the result of such a lucky or unlucky accident that the probability is 1 for the entire universe since its inception. One popular explanation comes from the classic Carl Sagan and Frank Drake side of the fence. They said Earth is nothing special. It's just another rocky planet in a humdrum system, in a regular old galaxy, and there should be plenty more like it. The universe is huge. Life must be everywhere. That's the principle of mediocrity in a nutshell. But there's another idea. Maybe Earth isn't mediocre at all. Maybe it's so one of a kind that the universe is basically a quiet void full of dead rocks. This "we are the only kid on the playground" vibe is captured best in the book Rare Earth by paleontologist Peter Ward and astronomer Donald Brownlee. They argue that complex life might be rarer than a winning lottery ticket. So what's the truth? First, yes, a planet needs to be in a star's Goldilocks zone, the distance that keeps water liquid. No liquid water, no life, as we know, simple enough. But many folks think that's pretty much it. Find a rocky planet in the right orbit, bam, you got life. Rare Earth says, hold your horses. That's nowhere near enough. Supporters of the unique Earth hypothesis argue that a planetary system capable of supporting complex life must inevitably be organized more or less like the solar system. Many are convinced that almost the only condition for the origin of life on the planet is the so-called zone of Goldilocks. It is also called the habitable zone. This is a region around the star where the condition on the surface of the planet orbiting the star will ensure the existence of water in the liquid phase. Liquid water is essential for life and is a solvent in many biochemical reactions. It is also unique in that the Earth's orbit around our luminary is quite circular, so again, we are never too far away or too close. And I repeat, many believe that if you find rocky planets in space that orbit their stars in the Goldilocks zone, then life on those planets is almost an inevitable consequence. But for life, as you soon realize, it's catastrophically insufficient. From the point of view of the authors of The Rare Earth, the habitability zone within its star is not the only habitability zone to be in. Our entire solar system is also lucky enough to be in the habitability zone of entire galaxies. It's not the most obvious thought, is it? Our solar system orbits the Milky Way center once every 235 million years or so. That means that since the ocean appeared on Earth, it's traveled all of this distance 17 times. Since the first reliable signs of life, 15 times. Since the first multicellular organisms appeared, about 7 times. And it's not just a relaxed flight, you know? The galaxy is full of terrifying things that are absolutely lethal to our tiny solar system, especially over its vast stretch of time. But living matter is still here. You see, most of any galaxy is a dead zone incapable of supporting complex life. The closer to the galactic center, the stronger the destructive effects of X-rays and gamma rays. It is produced by black holes and neutron stars, which are more numerous the closer we are to the galactic center. The closer we are to the galactic center, the more frequent are supernova explosions somewhere nearby. Another nice thing that can destroy entire world many light years away. There are lots of stars in galaxies, and even more planets around those stars. So life must be thriving all over the Milky Way. When we say so, we are rather mistaken, because the main mass of stars is concentrated just closer to the middle, which is not surprising. And it is there that the real butchery takes place. In addition, the high density of stars near the center or in the spiral sleeves of the galaxy means that there are also large gravitational disturbances. So even if we have a planet orbiting its star at an optimal distance, all that good setup will go to hell when some other star or worse flies by. In general, too close to the center of the galaxy is bad, but too far away is also bad. Moving away from the galactic center reduces the metallicity of stars, and metals are essential for the formation of Earth-like planets. Recent studies show that the galactic habitable zone is about 7 to 9 kiloparsecs from the center of the galaxy. Research shows only 5 to 10% of stars are in this sweet galactic band, where Earth-like life is even remotely possible. But the most important thing is time. A planetary system suitable for life must maintain stable and suitable conditions for billions and billions of years, in order for complex life to develop in it. Therefore, a life-supporting star should preferably have an almost perfectly circular orbit around the center of the galaxy, and in addition, its rotation rate should be synchronized with the rotation rate of the spiral arms, to pass through dense clusters of stars as seldom as possible. And yes, the solar system is exactly what is in the zone of habitability of the entire galaxy. And the orbit of the Sun around the center of the Milky Way is almost perfectly circular, with a rotation period of 255 million years, which roughly matches the rotation period of the galaxy. But that's not all. Our galaxy represents a pretty rare case, 10 billion years. The Milky Way hasn't collided with another galaxy for around 10 billion years. That's apparently quite rare. Only 7% of galaxies have this level of calm, giving any potential life billions of years to evolve without cosmic catastrophe. As you can see, even on such a huge scale, there are many nuances to consider if we want to understand how unique our galaxy is. Let's zoom into our neighborhood. We like to say, oh, every star is probably like our Sun. Yes, we all know that stars can be radically different in size, for example, but that's not the point. Up to half of the star systems in our galaxy are binary or trinary. For example, one of the most famous, the Polaris, which helps travelers find north. It's not just one star, it's a triple star system. Double and triple star systems look impressive, but they are almost certainly completely uninhabitable. In systems with more than one star, the stability and consistency of planetary orbits remains highly doubtful. It takes very delicate adjustments, or some special conditions for even a planet not inhabited by life, to exist normally among these titans. Our Sun itself is unique in so many ways because even if there is only one star, it is not a guarantee of stability. And for life to evolve, a star must be stable. The Sun's brightness only fluctuates by about 0.1%. And again, it is accepted to say that the Sun is the most ordinary star, of which there are countless. But for today, not found any star of Sun twin, on size, temperature, age, luminosity, and metallicity. I remind you that correct metallicity is necessary for the formation of protoplanetary disk, from which planets are formed, and also for small change of star luminosity. You ask, is the Sun some kind of absolute ideal? Yes, there are many variations here. For example, the larger the star, the wider its comfort zone for life, and therefore the higher the probability of the origin of this life. Well, yes, if we are talking about temperature. Bigger stars might have wider habitable zones, but they die young. Some only last millions of years before going red giant. For example, our beloved Betelgeuse is only about 10 million years old. By comparison, the Sun is 500 times bigger. Ignoring radiation, even the simplest life near supermassive stars probably won't have time to evolve. Smaller stars, like red dwarfs, can live for trillions of years, an unthinkable amount of time. Plus, red dwarfs never become red giants. That's true, but red dwarfs are pretty cold. Their temperature is just above the temperature of the filament in an electric light lamp, about 3000 degrees Celsius, and they are very dark. Some red dwarfs emit 10,000 times less light than the Sun, so a planet with the potential to develop complex life would have to be very close to such a star, and that seems cool, but there are at least two problems. The first is that a planet so close to a red dwarf will almost certainly fall into a tidal locking and begin to rotate around the star, turning to it forever only one side. It's called tidal capture, like what the Moon does with the Earth. So it will always be terribly hot on one side of the planet and terribly cold on the other. And as if it's not enough, the stellar wind, which in red dwarfs is not particularly weaker than the solar wind, will leave no chance for the development of life in the terminator zone. The terminator zone is that strip between light and darkness, where the temperature can theoretically be comfortable. Now look at the planets in our solar system. Do they look normal? Is there anything unusual about them? What about their arrangement? Is this even a typical arrangement of planets in planetary systems in the universe? We've got 4 small rocky planets followed by gas giants. That must be pretty common, huh? Well, it's not. We actually have a very strange planetary system. First of all, it has a very wide range of planetary characteristics, from tiny Mercury to giant Saturn and giant Jupiter. In most planetary systems in the universe, the planets are not very different from each other. Most planetary systems in space near a star have super-Earths several times bigger than ours. But here we have in the inner region of the solar system only a few small rocky planets, and none inside the orbit of Mercury. Secondly, gas giants the size of Jupiter or Saturn are rare and occur in only 10% of planetary systems. And these few very rarely have a stable, almost circular orbits so far from their star. And we have 2 of them, with rather large orbits at a significant distance from their star. We still don't really understand how this configuration of the planets in the solar system even occurred. There are all kinds of complex computer models being derived, but there is no consensus yet. Someone will irritably ask, what does this arrangement give us? Lots of things. Unlike most super-Earths in space, the size of the Earth is optimal. A planet that is too small, among other things, cannot maintain a sufficient atmospheric layer, so its surface temperature will be low and changeable, and oceans will simply not be able to appear. A planet that's too big will maintain a very dense atmosphere. Wait, so our neighbor Venus, while smaller in size, has a 92 times denser atmosphere than Earth, which makes its temperature about 462 degrees Celsius. This is true, and perhaps the early Earth once had a similar atmosphere, but then may have lost it in the catastrophic explosion that formed the Moon. This explosion subsequently allowed the Earth to acquire an atmosphere with optimal parameters, and its density differently compensates for daily temperature variations. The formed ozone layer protects the Earth's surface effectively from ultraviolet light. Nitrogen and carbon dioxide are in the right proportions for the emergence of life. Precipitation is necessary for the water cycle, and so on and so on. But we got distracted. It is this distribution of planets, where the gas giants are on the outer side of the planetary system, that gives the advantage. An advantage in the form of shield against asteroids. So yeah, you might look at yourself in the mirror and say, I'm not perfect. I've got this weird hair and a painful awareness that existence might be meaningless. But from the universe's standpoint, You're a spectacularly improbable piece of self-organizing matter, a cosmic lottery winner. Maybe keep that in mind next time you stare at the mirror. You're basically a symmetry-breaking cosmic miracle, with a questionable sense of humor. Congratulations. Enjoy it while it lasts. While I was editing, one very big thing came up in the news. Revolutionary discovery. Scientists have announced possible extraterrestrial life for the first time. The James Webb telescope, operated by a team of scientists from Cambridge, has detected substances in the atmosphere of the exoplanet K2-18b that are produced on Earth only by living organisms, dimethyl sulfide and dimethyl disulfide. This could mean that there is life on this planet. While this cannot yet be stated definitively, it is the strongest evidence we've had so far. In all the time of observations, no other planet has shown such precise presence of signs of life. This is a revolutionary moment. This is the first time humanity has seen potential biosignatures on a habitable planet. The amount of this gas in the atmosphere, we estimate, is thousands of times greater than what we have on Earth. If the connection to life is real, this planet will be teeming with life. If we confirm that there is life on K2-18b, it should essentially confirm that life is very common in the galaxy. The planet is located in the constellation Leo, 124 light-years away from Earth. To stay updated on more groundbreaking news, I'm posting all the big updates on my Telegram. The link is in the description.